Hey, wanna know a secret? Right now, this very moment, you are actually aging slower than everyone else in the universe. Your atoms are living life on fast forward compared to everything else. How can this be possible? Is it some new age mumbo-jumbo? Nope, it's science. More specifically, it's science that explains why time slows down in space. Buckle up for a journey through the fourth dimension. Because today, we are exploring the bizarre reality of time dilation. Do you think time always marches on at the same rate no matter where you are in the universe? Think again? According to Albert Einstein's theory of special relativity, time is not absolute, it's relative. Yep, that's right. The old saying time is relative turns out to be scientifically accurate, not just a figure of speech. In the grand cosmic dance, time is intertwined with space, forming a four-dimensional fabric called spacetime. This means that time isn't a tick-tock on the clock, but rather a flow experienced alongside the three dimensions of space. But here's the kicker. The flow of time isn't the same everywhere. It changes depending on your speed, and yes, even on how strong the gravity is where you are. Let's start with special relativity, which deals with time dilation due to motion. Imagine you are chilling on Earth watching a rocket take off. On the rocket are your twin siblings. Now both rockets blast off into deep space, each traveling at an incredible 99% of the speed of light, leaving you all alone on Earth feeling very unimportant. After a year passes, according to their chronometers, the twins decide to return home. Upon their arrival back on Earth, they step out looking years younger than you. Wait, what? How is this possible? This phenomenon is called the twin paradox, and it's a real consequence of special relativity. Here's how it works. As the twins approach the speed of light, time for them slows down relative to you on Earth. Since nothing can travel faster than light, the closer they get to that speed, the slower time passes for them. At 99% of the speed of light, time passes 7 times slower for the twins than for you on Earth. Therefore, after a year has passed for them, almost 7 years would have passed for you. So when they come back to Earth, they would be younger than you. Now you might be thinking, well, it's all relative. Who's to say whose clock is right? Well, Einstein said that the clock that S moving relative to the observer is the one that S ticking slower. In this case, since you are the observer on Earth, your clock is the one that's keeping time as usual. The twins on the spaceship are the ones whose clocks are running slower. You're probably wondering, if time slows down for objects moving at high speeds, would we be younger than everyone else on Earth? Because we re-spinning on a planet that S whizzing around the sun? Yes, but the effect is so minuscule we can't notice it in everyday life. However, we do have some pretty solid evidence that time dilation due to motion is real. In 1971, the Haefel atomic clock experiment took 2 complete rotations of Earth on commercial airplanes. These airplanes flew east and west and carried with them cesium fountain atomic clocks, which are incredibly precise. Upon their return, these clocks were compared to clocks that remained on Earth. And guess what they found? The clocks that flew eastward, moving faster, were slightly ahead of those that flew westward. The difference was small, but it matched exactly the predictions made by Einstein's theory of special relativity. But wait, there's more. Even if you're not blasting through space at near light speed, your location in space can still affect how time passes for you. Enter Einstein's general theory of relativity, which takes into account not just motion, but also gravity. In other words, the stronger the gravity, the slower the clock. This means that if you're standing on the surface of Earth, time would pass slightly slower for you than it does for someone far away in deep space, where there is virtually no gravity. Again, this effect is tiny and not noticeable in everyday life, but it has real-world implications. For example, GPS satellites orbiting Earth need to account for both special and general relativity to keep your location pinpointed accurately. Special relativity is used to correct for the satellite's high speed, and general relativity corrects for the weaker gravity they experience in orbit. Without these corrections, your GPS would be off by kilometers every day. Now, let's take a trip to the extreme. Imagine hopping aboard a spaceship and hurtling towards a massive black hole. As you approach the event horizon, the boundary of no return, time would slow down dramatically. From your perspective, time would pass normally, but for an observer far away from the black hole, your clock would appear too slow to a halt. If you were to cross the event horizon and venture into the heart of the black hole, time for you would essentially stop. You would be utterly cut off from the rest of the universe. This is known as gravitational singularity, and it's a place where the known laws of physics break down. So if you were to survive a trip into a black hole, you would essentially be flung into the future. If you managed to escape before being spaghettified, you would emerge into deep space and time, much further into the future than anyone left behind in the observable universe. Here's the kicker. You wouldn't even realize you had traveled into the future. Your own clock would still be ticking away normally. This is because time is relative. Only someone observing you from afar would see you leaping into the future. Remember the movie Interstellar? Well, the movie got the science mostly right. In the movie, Matthew McConaughey's character, Cooper, travels near a black hole and spends time on a planet there. From his perspective, only hours pass, but when he returns to the spaceship, he finds that years have passed for the rest of the crew. This is exactly what would happen in real life. While time dilation doesn't allow us to travel back in time, it does mean that we can travel forward in time. If you want to take a journey 100 years into the future, you would need a spaceship capable of traveling at 99.999% the speed of light. With the current technology, that's just a fantasy. But hey, who knows what the future holds? Maybe one day we will master the ability to control time itself. Until then, we are stuck in the present moment, and all we can do is marvel at the fact that time is not just a tick-tock on the clock, but a cosmic dance. A dance in which gravity and motion play their part. Time is not a simple metronome, but a symphony conducted by the very laws of the universe. And remember, you are a part of this cosmic ballet. Every cell in your body is affected by these laws. Every breath you take, every heartbeat, every thought you have is synced with the rhythm of the universe. So the next time you feel like time is slipping through your fingers, pause and appreciate that you are part of a grand cosmic clockwork. You are dancing with the stars and planets under the very laws that shape the universe. Thank you for joining us today. If you enjoyed this journey through time, don't forget to hit the subscribe button to join our cosmic dance. Together, we can explore the wonders of our universe. Until next time, keep looking up and keep questioning. Who knows? You might just find yourself dancing with the cosmos.